Hello, today I'm going to be showing you a partial fractions algorithm that can be used in a computer algebra system. Partial fractions is a very central algorithm for many different kinds of symbolic computations, such as integration and Laplace transforms. The algorithm I'll be showing you today is similar to the cover-up method you may have learned in school, but the main drawback of that method is that all the terms in the denominator have to have a power of 1, which isn't ideal. But this method can be any exponent. This will require a little bit of calculus, just repeated differentiation of certain functions, and also Pascal's triangle. Alright, so to show you what this algorithm does, just as a demo, I'm going to do the problem, say 1 plus 2x plus 3x squared over x minus 3 squared times x plus 7. So the numerator has a degree 2, 1, 2, 3, so that's 1 plus 2x plus 3x squared, and then the denominator had two terms. I had an x minus 3 squared times x plus 7, so 7 to the power of 1. So here's what we entered. And here's the answer it calculated. So you can see it generated all the numerators for each of the terms. And here's it comparing at different points, and you can see it works. Let's do another random one. So I'm going to do, let's do, boom. Let's do 3 terms. Let's do 3, 7, 2, 5. -1, 3. There we go. So here's what was entered, and then here's the full expanded form. This time I think is a bit of an overestimate. I think Java's virtual machine just has to load all the classes, so some of those milliseconds may have been. This might be an overestimate. As you can see, comparing at different points. Clearly it's the same function. So, and the fact that I'm using floating point is not necessary. Here I just created a generic number class which just defines a number. I'm using doubles, but you don't have to. I mean, you can use fractions, using big integers. It can be any kind of exact form. It's just that floating point was the fastest way to program a demo. But as long as you implement, like simple arithmetic operations like multiplication, division, addition, subtraction, and powers, it should just work. And so you could rewrite my number class if you wanted to and make this work. So, alright, so now I'm going to show you the theory behind how it works. Alright, so to begin, I'm just going to do a sample problem with the normal, well, not exactly the cover-up method, but basically the same idea. Alright, so that, breaks down to this and this. And to solve it, to solve for a, you'd multiply by this, both sides by this term. And then when you plug in the root of this, which is x equals 3, this will cancel away, and then you effectively solve for a. So you just substitute this at x equals 3, which is 4 over 5. And then to solve for b, you do the same strategy, right? You multiply both sides by this x plus 2, and then the root of this would be minus 2, and then you'd substitute it, and then this part would cancel away. Alright, so now let's do a very similar problem. Let's do x plus 1 over x minus 3 squared times x plus 2. Alright, so this would, break down. Now I'm going to multiply both sides by this x minus 3 squared term. So this becomes x plus 1 Now to solve a1, we could substitute the root again, which was x equals 3. And that gets wiped out, so then, a1 is equal to x plus 1 over x plus 2 when x equals 3. Alright, but now let's try to solve for a2. So I'm going to do something a little different. I'm going to take the derivative of both sides. So when we take the derivative of the left side, we get there. And we take the derivative of a1, that's a constant, so that becomes 0. You take the derivative of this, you get a2. And then I'm just going to leave this in derivative form. And when you take the derivative of this expands into two terms or whatever, but every term is going to have an x minus 3 in it. So when we substitute in the x equals 3 as the root, this will become 0. And so now you solved for a2. So a2 now. Alright, so now let's kind of generalize this concept. If we have this to the n times x plus 2, this breaks into a bunch of a1 over x minus 3 to the n plus a2 over x minus 3 to the n minus 1 plus so on until you reach the a of n term over x minus 3 plus b over x plus 2. So, and we can solve for each of these a's. So let's multiply both sides by this x minus 3 to the n term, x plus 1 over x plus 2 equals a1 plus a2 x and then plus b over x plus 2 times x minus 3 to the n. Alright, so we can solve for a1 by substituting the root, and then we can solve for a2 using the derivative of this, because this will go away, and then when you substitute this, all of these will still have a x minus 3 term. So we can solve for each of these by taking the nth derivative of the right hand side. So, the an now, because of these exponents, every time you take the derivative, it's going to keep adding that bit, so you have to divide by the factorial. And then we just substitute in at that root value, which is 3. And this solves for every a of n term. Here is kind of like the full formula. Hopefully I didn't make any mistakes. Basically, your input function, you take that in. And that's just the ratio of the polynomial over a product of binomial terms. Make sure the degree of the numerator is less than the denominator. And then that becomes the basically full expanded form of that. And for each of these terms, it turns into its own sum, where each of the where it decreases in power, like we saw in the last problem. This is just sort of the full form. And over here, this is just representing f over this product of terms without the current working term. So this would be like the current working term. This is, I'm multiplying it effectively to cancel it out, but you want to make sure this is simplified, otherwise when you evaluate this, you'll have it divide by 0. So this is just kind of saying that you're canceling out the term effectively. Alright, so that formula is great, but you have to take the repeated derivative of this, which is kind of a problem. If you try doing this symbolically, you'll get what I would call a symbolic explosion, where like basically every time you take the derivative of this expression just explodes in complexity. Every time you take the derivative, the complexity would just skyrocket. So we need a way to take the nth derivative of this in a reasonable time span. Otherwise, all the time your computer algebra system is going to be taking is taking the derivative of this, which is terrible. Alright, so how do we take the nth derivative of this, where the numerator is a polynomial and the denominator is the product of binomial terms? So let's just figure out how to get the nth derivative of the denominator first. So the denominator is in this form. So when you take the derivative of this, using the product rule, this would become this. And then the product rule expands to a bunch of sums where you take the derivative of basically every single one. So then the second term would be keep the first, and then b2 x plus a2 to the b2 minus 1, and so on with this portion. B and then plus, and then this expands. This is a very large expression, but you'll see it gets better. Let me just finish writing this. Alright, so this is kind of like the full expanded expression. Very messy, but can rewrite this in a much more compact way. So subtracting 1 in an exponent is the same thing as dividing, so I'm going to write this a little bit differently. So you get b1 over x plus a1 times, for this first term, we get the x plus a1, so the b1, and then for the second term we get b2 over x plus a2, and then we actually get the same expression again, which is the same as the original. I'll call this p. So really it expands into a much simpler expression where every term basically you can factor out a p. X plus n times p. So let's factor out the p, and then we get a sum like this. We get a sum. You can factor out the p out of every term. So we get p times bi over x plus ai, where I is from 1 to n. This is a product, by the way. Well, this is p prime. So we've found the first derivative of this expression. So now let's see if we can get a nth derivative for this product. So to get the nth derivative of p, we can use the general Leibniz rule, which basically defines the nth derivative of a product of two functions. I'm going to change the notation a little bit. I'm going to call the zeroth derivative of p P0, and then P1 would be like the first derivative, P2 would be the second derivative of P0. And this is just to make it easier to write. So as long as we can get the nth derivative of P0 and this sum term, then we can get the nth derivative of this. Now it's important to point out that these are numbers. Because we're evaluating the derivative at a single point and the same point, we can just calculate these as numbers. And as long as we can calculate the nth derivative of each of these as numbers, we can get the nth derivative of P0 at that x value. Alright, so I'm just going to do an example. So we obviously have P0 calculated already. That's just the binomial product. To calculate P1, which is just this, that's just P0 times this sum. I'm going to call the zeroth derivative of the sum as this sum symbol 0. Then P2 would be P1 sum naught plus P0, and then the first derivative of the sum. We can calculate the nth derivative of the sum pretty easily. So let's do that. The derivative, let's just do the first derivative of this sum, which is just sum naught. So that would be negative bi over x plus ai squared. So this would be the first derivative. Second derivative of this, since this is equal to sum 1, this would be, actually this would just be d over dx sum 1, which is same as the squared over dx squared of sum naught. And that would be then 2 over x plus ai cubed. So if you kind of keep doing this, you'll see a pretty simple pattern. Dn over dx to the n of sum naught, or this is the 0, so this will be negative 1 to the n times n factorial times bi over x plus a sub I to the n plus 1. So this is the nth derivative of this sum naught function. So we can calculate the nth derivative of that. And then what's interesting is that while we don't have P1 calculated, every time we take this derivative, we're calculating the new number. So we calculate P1, and then we calculate the second derivative. We've just calculated P1, so now we can calculate the second derivative of P0 using that value we just calculated. And so you just keep doing this, and then using general Leibniz rule, you can figure out how this expansion goes. Now it just follows Pascal's triangle. So, and it kind of just starts right here, right? This would be like the first row. So this would be 1. This is 1, 1. This I'm talking about the coefficients. For this third one, P3, this would be P2 sum naught plus 2 P1. Oh, sorry, this is P sum 1 plus P naught sum 2. And the coefficients for this would be 1, 2, 1. So this is like the next row of Pascal's triangle. And you can keep doing this. And, you know, this decreases every 1, this increases every 1. So that's kind of, it works the same way as a binomial expansion. It's the same concept. So we can calculate the nth derivative of p naught sort of by using the previous derivative's value. And these are all numbers. So you can just calculate the next derivative's number value by this pattern. Alright, so now that we've calculated the nth derivative of p naught, which is the denominator of the binomial product, our original problem though was to figure out the nth derivative f over g. So we calculated basically the nth derivative of just the g, but calculate the nth derivative of f over g. We can rewrite this as f times the inverse of g. And using the Leibniz product rule, as long as we have the nth derivative of f, calculating the nth derivative of a polynomial is very easy. But how do we calculate the nth derivative of the reciprocal using our current derivative table? So let's do that. So now that we have the nth derivative of g, let's get the nth derivative of 1 over g. So let's just call our function a. A naught would be the zeroth derivative of 1 over g, which is just 1 over p naught. A1 would be the first derivative of this, which is negative 1 over p naught squared times p1. This can be rewritten actually as a naught squared, negative a naught squared times p1. Notice that this is a product of two functions. Now there is a square here, there is a workaround, but we can calculate the nth derivative of a naught similarly to how we did above by the product, Leibniz product rule. So to get around this square, I'm going to define a new function called q. Q is going to be equal to a naught squared. But this can be written as a naught times a naught. This will be useful. So let's rewrite this as a negative. I'm going to call this q naught. Negative q naught p1. Now to calculate a2, just take the derivative of this. So we get negative q1, and we can actually calculate q1 because to calculate the derivative of q1, that's equal to a1, which we've calculated already. That's a1, a0 plus a0, a1, and every derivative of q is always going to be in terms of an a that we've already calculated, and it's just the Leibniz product rule since the product of two functions, which are a naught. So we can always calculate the next row of q right after we've calculated the last row of a. So we can calculate q1. So we get negative q1 p1 plus negative q naught p2. You'll notice that this is always off by 1, so I'm going to rewrite this in a little bit more simple way. So this will be negative a1 p0 plus 1 plus negative q naught p1 plus 1. So that way it kind of retains the form, we just have to add 1 to the index. So now we've calculated a2. So we can keep calculating the next row of a. So once we calculate this next row of a, then we can calculate the next row of q. And then with this new row of q, you can calculate the next row of a. So it's kind of like a back and forth between the two to calculate the next rows of a. Just have to make sure you keep track of those negative signs. So here's kind of like the pseudo code of how you would keep calculating the next derivative of a, which is just the nth derivative of 1 over g. So the algorithm really starts right here, and to calculate a1, you first calculate Pascal row, which is 1. Then you calculate the next q. So that would be just the initial row, right? So a0, 0. And then you calculate. Then from that q, now you can calculate the next required a, which would be a1. Then you do the next step, calculate the next Pascal row, which is 1, 1. Again, here 1, 1. You just factor out the negative, it would be 1, 1. And then, now that you've calculated the next q, now you can calculate the next row of a from that q. Because here, this row requires q1. It depends on q1. And then you calculate the next Pascal row, then you calculate the next row of q, which depends now on a2, which we've just calculated. Now that you've now calculated the next q row, you can now calculate the next a row. And you keep doing this as many nth derivatives of 1 over g as you need. And that's how you do that. Now that you have the nth derivative of 1 over g as a table, you have the tables for f, which is that polynomial. Very easy to calculate the nth derivative of just a plain polynomial. We have the nth derivative of this 1 over g function. Now we can calculate the nth derivative of their product using, again, the Leibniz product rule. So same algorithm as we've been using. And that's how you calculate the nth derivative of f over g. So that solves that problem. Alright, so now that I've shown all the theory behind how it works, I just want to show you sort of how my code works. So first I created a number class, which just defines, it just holds a number, and I implemented just basic arithmetic operations, addition, subtraction, multiplication, powers, and this value is hidden, so you can't actually ever access the double. This method is never used in the algorithm. This is just when you're entering in the value, but it's also kind of immutable. You can't change once you create a number; it stays that value. So that's the number class. And then I define a derivative table. This holds the list of derivatives, which is useful throughout the algorithm, all over the place. The 0th index would be the 0th derivative, and then the last one would be the n-1 derivative. So this just keeps track of all the derivatives as a number. Remember, the derivative is being computed at a point, so we can just calculate the number. So it holds numbers, like it doesn't hold an expression or anything. This generate Pascal row, you give it the current row, and then it'll generate the next, it'll basically modify this original list to generate the next Pascal row. So initially it's an empty list, and then it just keeps adding the next row. The reason why I don't use the choose function is because this is a little bit faster. The next class is just the binomial. The denominator is made up of a bunch of these. So the shift, so if you're like do x plus 1 squared, the shift holds the plus 1. I call that the shift. And then the exponent, which would be 2x plus 1 squared. So that holds the exponent. The exponent is always an integer, so there's no point in using number. Value at just calculates the value at the point given. This just returns the shift. This just returns the root, so that's just negative of the shift. This is used if you remember, substituting the root canceled all those terms, so the root is very important. The binomial product just holds a list of these binomial terms, and then when we calculate the value at a certain number, it's just the product. Calculating the degree, largest degree. I don't think these functions are used. I don't remember. Alright, so generating. So if you remember the sum, the nth derivative of that sum for the nth derivative of the binomial product, this is the sum portion. And then this is generating the actual nth derivative of this binomial product at a given value, and then how many derivatives you want. This generates, remember the 1 over g, this calculates the, given the nth derivative of that p0 function, this calculates the nth derivative of 1 over p0. So this just calculates the reciprocal. This is the Leibniz product rule. So you get the first table for the first function, and the second table for the second function. And then this just uses a combination of those two functions to do f over g. Then I define polynomial. Polynomial derivative table. So this doesn't store the numbers, it actually stores a list of the polynomials as a derivative, because they can be recycled over and over again. You're always going to take the derivative of the numerator, the same numerator. This is how the this is just the polynomial over binomial product, so that's like what your input function will be. Then number over binomial. So the sum of inverse binomials holds basically the inverses, so that's like your output. And then here's that giant calculation, which was done with the nested sums. This basically represents the nested sums. That's pretty much the whole algorithm. I'll put the code in the video as a link, so if you want to play with it.